and used to drive civilization. We like to think we're living in a bold new age of silicon, but the stuff that powers us is oil. Ancient, mysterious, and messy. There are now 6.5 billion of us on the planet, pretty much all relying on oil in some way every day, myself included.
Well, if it's so important, it's a bit surprising then that most of us don't know what crude oil really is or where it comes from. And this is a fascinating story with a sobering twist at the end that pretty much no one has seen coming.
Well, because all these geology stories begin, I visualize a warm, shallow sea. But that's where a lot of the rocks come from, where a lot of these things happen.
Basically, oil is formed from living material, from tiny, microscopic, in fact, plants that proliferate in the surface of the oceans.
They are definitely the beginning of the oil story. They are the material from which everything else subsequently evolves.
So they fall down onto the sea floor, and then the sediment builds up layer by layer by layer by layer by layer.
When we were exploring in the early days, when we found a black, stinky kind of looking shale, and sometimes it even smelt of oil if you cracked it open, we said, well, that seems a likely source.
All these men are geologists who have been involved in finding the oil we use. And this was about the limit of what they knew only 20 years ago. Back then, locating oil reservoirs was much easier than explaining where the precious liquid hydrocarbons had come from. Now, a deeper understanding is emerging.
To find out what separates a supervention algae from a barrel of crude, we need to negotiate an unlikely sequence of improbable events, stretching across a gulf of unimaginably deep time. But like every good epic, this one has a central character. It's incredibly ancient, impossibly small, and we're all full of it. It's carbon.
Carbon. Our bones and bodies would not exist without it, nor would plants or microbes, or the incredible carbon chemistry that links us all together. Carbon is the stuff of life on Earth. And it is old. Carbon was forged in the nuclear furnaces of long-dead stars before our solar system was even a wink in the celestial eye. This means every atom now on Earth has been on a restless adventure since the dawn of time. And that as far as carbon is concerned, every life form on the planet, us included, is 100% recycled and recyclable. Right now, about 1 trillion tons of carbon are bound up in living organisms. But far more is locked away in the fossil fuels like coal, oil and gas, and in the very rocks of the Earth, deep underground.
Of course, the carbon in you and I, and the air we breathe, is older than the Earth itself. But we can start this story of carbon, the crude story, in the fiery mouth of an active volcano much like this one, on a very different looking planet, a long, long time ago.
Back in the mid-Jurassic, the Earth was a dinosaur-inhabited world on the move. The continents, once joined together, were now breaking up. And the sustained volcanism pumped massive amounts of carbon into the atmosphere. Enter our central character, a single atom of carbon. It's been pumped out as a carbon dioxide molecule, joined at the hip to 2 oxygen atoms. It may be just one in a swarm of countless zillions, but it's as good a guide as any to take us through this oily adventure. As a gas, carbon dioxide helps set the global thermostat in the comfortable range. Too little carbon dioxide in the atmosphere and the entire planet will freeze. Too much and it will cook all over. And the Jurassic Earth is cooking. Hugh Jenkins is an Oxford University geologist. He spends a lot of his time with his head back in the Jurassic, trying to fathom where all the carbon was going and what the world was like all those years ago.
Well, I guess for half the globe would have been blue, studded with clouds, and the other half would have been brown and green.
From orbit, you would have seen the continents bunched together on one side of the planet, with the land to the north and south separated by a warm, ancient ocean called the Tethys. There were plenty of clouds, but no great ice caps at the poles.
As far as we know, there was no substantial ice on the planet, so it would have been a warm, what we call a greenhouse world with elevated levels of carbon dioxide. Imagine, if you will, a sort of gigantic Bahamas extending right over large tracts of what we call today the Middle East. That part of the world, you'd have a lot of shallow water carbonate environments, so not so different from the barrier reef. Obviously, there are the marine reptiles, and there are the land-loving reptiles as well.
It was into this greenhouse world that our carbon atom had been released. Now it was one of the many CO2 molecules helping to keep the climate of the dinosaurs hotter than any other period in the planet's history. For perhaps 100 years, it swirled through the landscape, over oceans and deserts, mountains and lakes. Eventually, it drifted into a primeval Jurassic forest. It spent a season inside the leaf of a ginkgo tree, and another 50 years in the body of the dinosaur that ate it. It passed from plant eater to meat eater before being exhaled back into the atmosphere, once again as carbon dioxide. Our molecule drifts on, and finally is swept out over the ancient Tethys Ocean. One day in the future, this warm equatorial seascape will become the oil-rich deserts of the Middle East. But now, the sea is rising, and so are the temperatures. Both the atmosphere and the oceans are loaded with CO2. Our molecule slips into the sea to become food for a phytoplankton cell. Trillions of these tiny plants swarm near the surface, all soaking up the sun and sucking in CO2. Inside this cell, our carbon dioxide molecule is transformed into an energy-rich sugar via the flash of a prehistoric sunbeam. As a means of capturing solar energy and storing it for later use, Photosynthesis is brilliant. The cell divides, and then divides again. Sunlight and carbon dioxide are being harvested and squirreled away into organic cell walls and fatty carbohydrate molecules. The whole Tethys Ocean is blooming with phytoplankton. Jump forwards to our modern world. The individual algal cells in a phytoplankton bloom may be microscopic, but en masse, you can see them from space. Giant green swirls appear in places where plant food is concentrated by winds, currents or rivers, or trapped by restricted circulation. If you go to one of these places, you can glimpse the beginnings of the process that formed oil in the past, happening in the ocean today. I'm heading into the Gulf of Mexico, offshore from New Orleans. The waters here have a bit of a nutrient problem, courtesy of the Mississippi River. Every spring, a flood of plant food in the form of nitrogen and phosphorus washes out into the warm Gulf waters from the farms and cities of Middle America. Warmth, sunshine and fertiliser. The perfect trigger for a bloom of phytoplankton. Once a month, a research team monitors the changing water conditions. I follow them into the pea green soup. As summer progresses, the waters here are overwhelmed with planktonic algae and bacteria, rich in organic hydrocarbons.
The important point is when you change the nutrient loads, you change what's growing in the water. And high nutrients favour those organisms that are ultimately going to lead you to a black, stinky black mud and ultimately a black shale.
There are so many dead and dying plankton cells sinking down that their decay starts to use up the oxygen in the water below.
And if it removes all that oxygen, those deep waters will become anoxic. They're devoid of oxygen. And you'll start to screen out a lot of the organisms that just can't live.
As we drop into the increasingly stagnant green gloom, the leg of an oil platform becomes our only reference. From about 10 metres down, we enter what local fishermen have dubbed the dead zone. They find nothing alive down here to catch. A steady rain of microscopic bodies is now sinking uneaten towards the stagnant seafloor below.
And if there are no organisms there churning it up, moving it around, then essentially you have this sort of millimetre, layer by layer of accumulation of mud.
"300 metres below perhaps the most fertile region of the ocean today, the water is anoxic, totally devoid of oxygen. A steady rain of dead plankton cells has accumulated into a thick, quivering, uneaten, black organic ooze. And another step on the long road to an oil deposit is complete.
Many of the petroleum source rocks that we see in the geological record accumulated in these extremely unhealthy environments.
And so they did in the seas of the Jurassic Middle East. Even at the surface, there was little oxygen in the bath warm water. Below lay a dead zone that stretched at least as far as Western Europe. Our carbon atom, bound up inside its dead planktonic host, settled into the stagnant darkness, along with billions and trillions of other little hydrocarbon-rich corpses.
The oceans then were just replete with organic matter. These microscopic plants proliferated in quantities that the world hasn't seen for millions of years. And they were also able to be preserved because these oceans were very prone to stagnation. So there was much less oxygen in the water, much less overturning of the water. The organic matter would sink to the bottom and be preserved, and then it would be buried by rapidly accumulating sediments.
This is what such a plankton graveyard looks like today. Mountains of black rock.
Well, here at Kimmeridge Bay in Dorset, we have the so-called Kimmeridge clay. And this is a black shale mudstone. So this is made up of the remains of plankton and clay, all these fine particles that have fallen through the water column and accumulated on the sea floor. If you look at these sediments in detail, you often find they're finely laminated. So there have been no animals churning them up, mixing them. The layers are just as they were when they were deposited during the late Jurassic.
These fine black shales have made southern England's Jurassic coast famous for the exquisite preservation of large animal fossils. But most people don't realise the shale extends deep under the country to the north and underpins the UK's bottom line as well.
Here at Kimmeridge, it's not mature, it's not been buried deeply enough to generate oil, but this, if you like, does the business in the North Sea. So this is very, very important for the whole economic well-being of the British Isles.
If you harboured any doubts that oil really does come from rock, you could always try this quick test. This is a bit of immature oil source rock, the Kimmeridge clay, and this is a small flame. Put the two together, and in a few moments, the rock starts to splutter and burn. It's not a raging inferno, but that smell from the blue smoke is unmistakable.
It's astonishing to think that what's burning here is fossilised Jurassic sunlight. But as a lump of rock, it's not much use for filling up your petrol tank. To drive out the oil, it needs to be cooked slowly in the moderate oven of the Earth's oil kitchen. And to enter the kitchen, the rock needs to be buried deep underground.
When it gets to a certain depth of burial, some thousands of feet below the surface, it's physically cooked by the pressures and the temperatures you get there, and the organic carbon cracks and goes from this original material to light sweet crude, as oil people tend to call it.
The temperature is critical. Bury the shale too far down and it is overcooked into natural gas. Too shallow and you end up with a half-baked greasy oil shale. Deep below Saudi Arabia, the conditions were just right, like a hot pot of tea for millions of years. Light, sweet crude containing our carbon atom began to flow like warm honey from the buried source rock. Of course, the Earth did not stay still while all this happened. The continents continued to break up and move. Mountain ranges rose and fell. Seas evaporated and returned. The face of the Earth changed completely. Around 15 million years ago, the Tethys Ocean finally closed up as Arabia collided ever so gently with Eurasia. The Tethys did not disappear entirely. Much of it simply folded and crumpled. Here in the magnificent desolation of Oman's Al-Hajar Mountains, the evidence of collision remains stark and dramatic. Welcome to the bottom of the ancient Tethys Ocean today. Baking hot, bone dry. Here in the Arabian Peninsula, there are kilometres and kilometres of these ancient marine sediments laid down right through the age of the dinosaurs. But there are a few places where you can walk on its surface. Here in the Hajar Mountains and in the Tuwaiq Mountains in Saudi Arabia. Pretty much everywhere else, it's buried deep beneath the desert sands. Three times during the reign of the dinosaurs, once in the Jurassic and twice later in the Cretaceous, thick black shales were laid down in the Middle East. So much that 2/3 of the world's oil comes from organic sediments buried here alone.
In Saudi Arabia and Kuwait and the 5 main Middle Eastern states, there were really singular conditions. You had a number of things that absolutely are required for giant oil fields. Really rich source rocks from which the carbon can be cooked at the right temperatures and pressures underground. Really excellent reservoir rocks where the oil can migrate through the microscopic pores and be trapped in these reservoirs. Really good so-called cap rocks. These are the impervious rocks over the reservoir rock that actually locks the oil in place.
Did you see the white color here?
And finally, really gentle structures, folded structures, anticlines, geologists call them, in which the oil could sit. Most people don't realize this. They think you can find oil anywhere. The vast majority of the planet is actually devoid of oil because these special conditions are not met.
Against these odds, the crude containing our carbon atom seeped ever upwards. It oozed slowly through the most porous and permeable rocks available, like ink in blotting paper. Eventually it could go no further and trickled into the limestone pore spaces of the largest oil reservoir on Earth. And there it stayed, trapped until humans came along. The sludgy remains of tiny, brainless plants waiting to hold dramatic sway on the future of the most intelligent life form the planet has ever seen.
I love oil. I think it's one of the most important elements, materials in modern society and civilization.
95% of the goods in shops are there in some degree because of oil or contain oil or are derived from oil.
When do we first start running out of oil? Well, in fact, we started when we produced the first gallon.
If you try to imagine living without cars or airplanes or air conditioning or any kind of product made from oil, you just can't possibly conceive of it.
we've allowed ourselves to become completely addicted to this stuff. I mean, it underpins virtually everything in society.
We're using it up in, the blink of an eye. In the blink of an eye, we've used up nearly half of, that's incredible to me, how fast we've done it and how long it took to make this stuff.
No one knows for sure when humans first encountered oil, though it was certainly at least 3,000 years ago, and probably here, in the lands of the ancient Persian Empire, where the chemical remains of fossilized sunlight still wind their way to the surface.
Of course, it's not only oil that can escape from the ground. This is Yana Dağ, or Burning Mountain in Azerbaijan, and the natural methane seeping from the earth here caught fire over 50 years ago, and it's been burning ever since.
Today we see such a display as evidence of a possible oil deposit nearby. In the days of the Persian Empire, it was a sign of the gods. The Zoroastrian religion, like its eternal flames, survives to this day. Fire temples were built around natural vents like this one near Baku. Worshippers heard the hisses of the natural gas as the talk of spirits, and saw the constant flames as the divine manifestation of truth. It seems wherever oil was encountered, people found a use for it.
It had a value as pitch. They would heat it, melt it, and then coat their boats with it.
They would throw it into water and see whatever shape it took would tell them something about the future.
The Chinese had a complete industry long before Christ. They had pipelines made out of bamboo, and they had junks that carried oil.
The Greeks would mix it with sulfur and put it in a clay pot, light it on fire, and it's essentially a bomb, an oil bomb.
They'd dump it overboard and set fire to it and burn the enemy ships.
In the Middle Ages, they discovered that they could use oil to make flamethrowers out of it.
By the 1800s, one enterprising American was even flogging it off to drink as the ultimate cure-all tonic. But in the end, it was a shortage of sperm whales that finally kick-started the oil age. With the price of whale oil skyrocketing, the discovery of how to distill kerosene from crude created the first global demand for lighting. From Baku to the backwoods of Pennsylvania, there was money to be made pulling oil from the ground quickly and cheaply.
Everything came together in August of 1859. There was the refining process, there was the lamp that could burn kerosene without giving off too much smoke, there were the financiers in New York and Connecticut that had the land and the money, and there was Edwin Drake, who was a retired railroad conductor who was in poor health, who needed a job. The first few times that they tried drilling, the hole kept collapsing on them. And so he got the idea of sending up to Erie, PA, for a big piece of steel pipe. And they drove that into the ground and then started drilling through that.
At 69.5 feet, they struck black gold. Crude oil began to surge up the pipe. Drake may not have been the first person to drill for oil, but it was here, down this very hole in the ground,
that he unleashed the oil genie once and for all. And it's no exaggeration to say, but what happened next in this quiet green valley in Pennsylvania changed the world forever.
Even though that first year they only produced 2,000 barrels of oil, it was still a marvel. And by the 1880s, Pennsylvania was literally the leading oil-producing area of the world. Over half of the world's oil came out of Pennsylvania.
The oil genie was now fully out of the bottle and into the barrel.
People had rigs everywhere, thousands of rigs, as far as you can see, because it was just, everyone was just hoping for the jackpot. It took less than a couple decades to drain most of the oil out of that state, and they moved on to Ohio, they moved on to Indiana, they moved on to Oklahoma, so it kept sort of wildcatting all over the place.
When Thomas Edison switched on his electric light bulb in 1879, he simultaneously switched off the demand for kerosene. The emerging big oil monopolies like J.D. Rockefeller's Standard Oil Company needed to find a new market for the oil they were swimming in. And it didn't take long to find one. It was the internal combustion engine, and it had a thirst for a waste product of the kerosene business: gasoline.
The automobile came along roughly 1910, and by 1920, Ford was mass producing automobiles, and this was when my mother claimed that the world changed for them, that the farm and the people who lived on the next farm weren't the horizon anymore. She went away to college.
Ex-shellman Ken DeFaze was a direct witness to the unfolding revolution.
Well, I was born right in the middle of the Oklahoma City oil field, and my father was a first-generation petroleum engineer. If I was a good boy, I got to go to the field with Daddy on weekends, and he could explain about the pipe and the derrick and the mud. And when I took petroleum engineering at the Colorado School of Mines, the professor opened by stating, "We date the birth of petroleum engineering from the invention of the bottom hole pressure gauge." I about fell out of my chair because my father and three other guys cranked the first one by hand into a well in Oklahoma City in 1927.
From the 1920s onwards, the oil and automotive industries worked together to help the world choose its future. As the price of crude fell, petrol-driven vehicles became more competitive than the electric cars that preceded them. Electric tram companies were bought out and the tramways dismantled. Bicycle pathways were abandoned and governments persuaded instead to build paved roads and highways for cars.
Before we knew it, we'd all moved out to the suburbs, we were all getting completely addicted, and we were designing economies built around this stuff, every sector of every economy.
We were seduced by convenience and power. As an energy source, oil has no equal. Like wood and coal, it would burn in air. But as a liquid, it's easy to transport. And the power of ancient sunlight stored in the strong bonds between carbon and hydrogen atoms can release 100 times more energy than it costs to get it out of the ground.
The thing about oil is it has incredible energy density. You know, the old question which the schoolmaster puts to the class: what will fill a teacup and lift a ton 1,000 meters into the air? And the class looked vacant. And of course, it's petroleum. You can put that much in a car, and you can drive up 1,000 meter hill, and you get there. It's an astonishing amount of energy in a small volume.
Put Royal Triton in Cynthia's little tummy.
Right, lady.
Cynthia will just love that Royal Triton.
The energy-rich hydrocarbons made engines and transport the obvious use for oil, but far from the only one.
There was one T-shirt that says, what else is oil used for? The ink on this T-shirt. The T-shirt. There are hundreds of different hydrocarbon molecules of different shapes and sizes in a single sample of oil. So the first task of a refinery is to sort them out. So the first big thing was to modify it for automotive gasoline and even more demanding aviation gasoline. Then diesel fuel came along, then jet fuel. Then the refiners started to develop ways of taking the bigger molecules and cracking them in half, or taking the smaller molecules and gluing them together.
And in this way, the modern petrochemical industry was born. About 10% of all oil is now converted into pretty much everything, from plastics to paints, from pesticides to painkillers.
We're born into these, in the sterile rooms. The plastic gloves catch us as we come out. We're swaddled in polyester, and then we live our lives bathed in oil.
Sonia Shah is a journalist, not a geologist. It was while researching a book on crude that she came to realise how deeply oil has seeped into our modern lives.
Some drip of oil has entered into almost everything we do.
What's happened a lot of times now is even simple foods have become more and more complicated because people need things to be convenient. The so-called value added, which means a lot of petrochemicals and petroleum products. These vegetables, I would suspect, are all grown quite far away from where we are right now. So they've been sitting on refrigerated trucks for several days, burning diesel, on our asphalt roads, and the whole thing's wrapped in, in a hard plastic. This is a natural food that has oil added to it. The average American uses about 3 gallons of oil every day. And that's probably a gallon for travel, a gallon on their products, and a gallon in their food.
From, our food to our clothes to our medicine cabinets to our toothpaste, it's really everywhere.
Even if you don't think a product has oil in it, it probably does. From the nets of fishing boats to the fertilizers on farms, petrochemicals have become indispensable components of human society. And oil, the fuel of choice to move everything around. But what if this river of crude was to slow? It would take a brave man to suggest that the bounty of oil had a limit, especially back in the 1950s. Especially a man in the business. Marion King Hubbard was a geologist of fearsome intellect and strong reputation. He worked at the Shell Research Labs with Ken DeFace.
One of the standard expressions around the Shell lab, and I think it had been borrowed from another source, was, since that Hubbard is a bastard, but he's a higher bastard.
The question of how much oil do we have is a matter of evidence, not anybody's opinion.
By 1956, Hubbard had become convinced that oil production from US wells would peak in the early 1970s. And he was going public.
The company said that, look, our position is we can find plenty of oil, just give us the right tax advantages and access to the drilling sites, and we'll keep you in oil, forever. He gave the first talk with the management of Shell Oil on the phone until 15 minutes before he went on the platform saying, don't do it, don't do it, don't do it. And he did it.
Shell's management needn't have been so concerned. Few people paid Hubbard's predictions any attention. And why would they? A bottomless barrel of oil had now been found under the shifting sands of the Middle East. The endless sunshine from an ancient world would be ours for the taking. Dr. Nestor Sander, now 92, is the last surviving member of the team of oilmen who found crude in Saudi Arabia. Today he lives in a modest house in Modesto, California.
I'm just a workman. I got a penny for every barrel of oil that's been produced. I wouldn't be sitting here in Modesto. I started out way back in 1938. I was there 6 months after oil was found in Saudi Arabia.
Back in 1938, after 4 years of dry holes, a shallow test well had shown oil was present in Saudi Arabia. Nestor's team was brought in to find out just how much and where.
I started out as a junior micropaleontologist whose job was to locate the traps where oil might accumulate. Oil is lighter than water, so that when oil migrates, it has a tendency to go up.
First, Nestor pinpointed the giant Abcake field.
Finding a new well that produced 7,000 or 10,000 barrels a day every 2 or 3 months was a heady feeling, I tell you.
But there was a bigger surprise to come. Nestor turned his attention to a geological structure known as the Gawar Anticline.
After the wells at either end of Gawar had been drilled, the company knew that it was onto something tremendous.
Nestor and his fellow oilmen had uncovered the treasure trove of the Jurassic Tethys Ocean. The Gawar field would prove to be the largest oil field ever found on Earth. A supergiant, it was 35 kilometres wide and 175 kilometres long.
In terms of global resources, it's one of a kind. I would say the North Sea, for example, would be 1/10 of Gawar by itself. The entire North Sea.
Somewhere down inside the pore spaces of the Gawar Reservoir was the carbon atom we met earlier. It had now waited over 160 million years to see the light of day. Just a few more, and it would be free again. The world has been awash with oil ever since the massive deposits were uncovered in the Middle East. Everyone wanted a slice of the action. The Soviet Union moved into the Caspian Sea deposits near Baku in a big way, pumping dry one well after another.
I've been sitting here since 8 o'clock this morning. How about I didn't go to work yesterday because I had no gas?
There's no need for panic or panic buying along lines we've seen on TV.
There was a little pandemonium at the pump during the oil crises of the 1970s, but it didn't slake the planet's thirst for oil, growing steadily at about 2% per year.
Stop the line, you're going to have to go around the corner. The line starts at the next street.
And shut out of the Middle East by OPEC, the big Western oil companies simply turned up the heat elsewhere. Rigs began pumping oil from technically challenging areas such as the North Sea, the Gulf of Mexico, and beneath the Alaskan permafrost. There were concerns, of course, about air pollution and oil spills. But the world was yet to start worrying about global warming and the end of oil.
Once the oil from those fields started coming online, we kind of forgot about all that other stuff, because now the oil fell to cheaper than a bottle of water. By early 90s, we were still buying cars faster than we were actually making babies. So the car population was starting to overtake the human population. But it kept going on anyway, because there's a whole romance of the car, which had been built up through the 50s.
This was always going to be a love affair on borrowed time. Just as Hubbard predicted, the United States oil reserves had peaked in 1970.
It was that peak in 1970 that turned Hubbard into a folk hero. I came home and told my family, old Hubbard was right. We got no unused production capacity in the U.S. anymore.
Before he died, Hubbard predicted global oil production itself would peak in the year 2000. Plenty of industry insiders now think he was pretty close to getting it right. Colin Campbell is another retired oil industry geologist. After a career spent unlocking oil in the North Sea and the Americas, he started delving into the state of the world oil supply.
I think we need 3.
It was enough to drive him into his local for a badly needed stout or 3.
Well, now we face the other side of the coin, the second half of the age of oil, when this stuff declines. And with it, I suggest, more or less the world we know in a strange way.
My God. Oh, excuse me.
Colin Campbell sees us living in a very glass half empty kind of world. And he's not alone.
Yeah, I was there at the beginning, yes, shortly after the discovery of oil in Arabia. And I'm seeing the end approaching. It's coming, undoubtedly. You yourself have seen it. The price of a gallon of gasoline has gone up 4 times. It'll go up 10 times.
Right from the beginning, the oil story has always been full of big numbers, but never more so than now.
Imagine for a moment a gigantic building full of oil. It's enormous, 1 kilometre on each side. Now look up. It towers a staggering 4.5 kilometres into the air. It's a tank of oil that would dwarf any city in the world.
This is the volume of oil we burned in a single year in 2004. 4.5 cubic kilometres of the stuff. Each year we guzzle another building like this, and each one climbs another 10 stories higher. Every day now, over 84 million barrels of oil are transported and burnt.
We go from 84 million barrels a day now to 110, 120 in 15 or 20 years' time. That's what everybody's assuming, all governments and all companies, all markets, but a growing body of us ex-geologists and current geologists who work in and around the oil industry who study this problem think it can't be done. That in actual fact the peak of production is really close. I believe it's 2008, plus or minus 2 years.
It could have been as early as mid-November and as late as January 6, 2006. But my line is, it's past. It's gone. My career as a prophet is over. I'm now a historian looking back at the peak.
My numbers actually say last year, but it could be this year. And if you consider all categories of oil, including the tar sands and the deep water and so on, I think 210 would be a good estimate. But really, it isn't. This peak has no great significance. It is the perception and the vision of the long decline that comes into sight on the other side of peak. That's really what matters.
We're dependent all of a sudden on rapidly shrinking supplies of ever more generally expensive oil. And that is the shock that's going to come to economies and the shock that will force us to go to the alternatives as quickly as we can.
The most optimistic market and industry voices still see the peak far off in the future, if at all. They point to growth coming from new technologies, unconventional deposits such as the tar sands in Canada, and new discoveries. But there are few corners of the world left to look in. In the US, the steel legs of thousands of rigs have marched right across the Gulf of Mexico. They've moved so far offshore, they're now out of their depth. Semi-submersible rigs are drilling in over 2,000 metres of water.
This comes as a big surprise to people who don't know the issue. With all its resources and its money and its incredible kit, the year that the oil industry discovered the most oil in 1 year that it ever will was way back in 1965. And it's been kind of downhill ever since.
After supplying the world with oil for over 50 years, even the mighty Ghawar oil field is showing its age. It still pumps half of all Saudi Arabia's massive output, but its own reserves have dropped by nearly 50%.
There's no question that the oil in the future is harder to extract than the oil that we have produced up to now. We've produced the best oil from the easiest reservoirs and the most convenient locations. We've produced over 1 trillion barrels of oil already. And at the end of the day, we have to ask, have we been producing it wisely or using it wisely in any case? And maybe we should be more efficient.
For the most part, oil is invisible to us. We barely see it, we rarely smell it. We have no real feeling for the enormous quantity of the stuff that fuels our existence. And we give little, if any, thought to the epic journey it's made from an ancient ocean to a tailpipe near you.
Perhaps it was me. Perhaps it was you. But somebody, somewhere, has just released our carbon atom back into the atmosphere. And it could well have been the halfway atom, the one that marks the peak of production. Though that may prove to be the least of our problems. Now the crude story comes full circle, with our molecule back to its old tricks, playing around with the climate. The oil genie has granted us our wishes. Immense power, untold wealth, and a hoard of treasures. But now it seems we must pay the price. Hidden in the black magic of an oil reservoir is a climate demon from the distant past. And we unleash it at our peril.
What we know for sure is that we're doing something which will have consequences that we don't like. How bad those consequences will be, we can't quite tell.
Once you extract the oil and you start burning the oil, obviously you're displacing the equilibrium and you're pushing carbon dioxide back into the atmosphere, which we've been doing since the Industrial Revolution, I suppose, and forcing the Earth towards a new greenhouse future.
We would go back to a world that is weirdly going to be quite similar to the world in which the oil formed in terms of temperature, state of the oceans, and so forth. So that there is a certain irony in this whole story.
To see our road to the future more clearly, we must first return to the past. We're heading back to the Jurassic, back to the steamy world of the dinosaurs, back to when the sand was sea. It was here, in the 100 million year interval between the early Jurassic and the mid-Cretaceous, that the vast majority of the world's oil was formed. But what was so special about this time? We know that the key to creating an oil deposit is for masses of organic rich plankton to fall onto a stagnant seafloor. This is how you end up with the stinky black mud that becomes the petroleum source rock. Simple enough. But this went only partway to explaining the huge size of the deposits that the geologists were finding. There was a puzzle here, and a link, it seemed, to some sort of global calamity. The first clue lay hidden in the Apennine Hills of central Italy. From the days of the very first dinosaur to the last, this whole rocky landscape was mud at the bottom of the sea. In the early 1890s, a wandering geologist noticed a discrete band of black organic-rich shale, sandwiched between the otherwise normal limestone.
This 1 metre of black shale was little more than a curiosity, and it might have remained just that were it not for one very important factor, and that is the discovery in the Pacific Ocean in the early 1970s of black shales just like this one, of identical age. So all at once, people began to realize that this was not a local phenomenon, but it was a global phenomenon.
It was a revelation. Up until this point, geologists had explained oil source rocks only in terms of specific local conditions, say a particularly fertile stretch of coastline or a naturally stagnant patch of sea floor. But here was evidence of something much bigger going on. Something big enough to suck the oxygen from oceans right around the planet. It's now thought that the world's richest source rocks and the most prolific oil regions are largely the result of these episodes of near-global ocean stagnation, the so-called oceanic anoxic events. And there was another clue hidden in the rocks, the full implications of which are only now being teased out. Each oceanic anoxic event was linked to a super greenhouse world.
Now, we know that the whole of the Jurassic and the Cretaceous was a warm greenhouse period, but there seem to have been periods or intervals of unusual warmth within that background greenhouse, if you like, to which these events correspond in time.
What we find out is that those intervals of time are these super greenhouse climates, and they were very different worlds. They were ice-free worlds, and we seem to have good supporting evidence for high atmospheric CO2 levels as well.
If you look at these times, these oceanic anoxic events, they seem to correlate with intervals of excess volcanism. And these huge outpourings of lava would have vented sulfur dioxide and carbon dioxide, and of course the latter would have promoted global warming.
The lead-up to every super greenhouse and matching oceanic anoxic event was the same. So the critical question for us becomes, how much carbon dioxide does it take to trigger such dramatic changes? That answer can be found in the ancient plants and their descendants still found growing today, like the amazing ginkgo.
Here we have a ginkgo plant. These essentially evolved about 200 million years ago, and we can see they have a very distinctive leaf shape. And essentially these probably formed a major component of the diet of dinosaurs through the Cretaceous and Jurassic. If you compare one of these modern leaves with a fossil ginkgo leaf, they're almost identically the same. And so by looking at the structure of this leaf and the chemistry of it and the fossil leaves, we can actually more accurately reconstruct the environment and climate at that time.
Living ginkgo plants can be grown under both modern and prehistoric conditions. Like all plants, they take in CO2 through microscopic pores in their leaves. The more carbon dioxide in the air, the fewer pores the leaves need.
Thank you, Holly.
Comparing pore numbers between living and fossil leaves gives a measure of how much CO2 was swirling through the ancient forests.
We find out, based on these plant fossils, that CO2 levels were about 4 to 5 times greater than they are today.
Four or 5 times more CO2 than our pre-industrial levels gave you seas so warm you could swim at the South Pole. But don't think of the planet during a super greenhouse as one big tropical paradise. This was a world dangerously out of kilter. As temperatures go up, so does the rate of evaporation and the humidity. The obvious result was more rain, falling heavily in powerful tropical storms. The rain, when it came, would have been more acidic than today, burning vegetation and etching into the rocks and soils. This probably explains the sudden flood of plant food into the ocean.
So huge amount of warming, huge amount of evaporation, lots of clouds, lots of rainfall, swollen rivers wending their way down into the ocean, bringing sediment, but also bringing nutrients like nitrate and phosphate, the sort of things you'd pour on your pot plant to make it grow in a more sort of spectacular way. These also fertilize the oceans, and they encourage the plankton, and they encourage particular types of plankton, particularly organic wall plankton and bacteria that go to make up our black shales that become our potential petroleum source rocks.
Such a flood of nutrients and the plankton blooms it triggered might have been enough to begin an anoxic event on its own. But in a super greenhouse, the overheated oceans were already primed for stagnation. Today's well-ventilated oceans rely on the planet having ice at the poles. It's here that warm, salty water flowing up from the tropics cools down, takes on oxygen, and sinks back into the depths to begin the return journey. This is the engine that drives ocean circulation.
The ocean mixes itself on the order of every 500 years or so, and it's that mixing process that brings oxygen into the deep sea. The warming that takes place as a result of the buildup of carbon dioxide is more dramatic at high latitudes. The supply of oxygen depends on there being cold water there. Warm water doesn't hold large amounts of oxygen in it, and so to provide oxygen to the deep sea requires cold waters where these deep waters are sinking.
In the lead up to a super greenhouse, there was no cold water at the poles. With both faltering currents and over-fertilised surface waters, the stage was set to push large areas of the global ocean, first into runaway anoxia, and then into something far more dangerous. Remove all the oxygen from the water, and deadly poisonous hydrogen sulfide will start to spread upwards from the stagnant depths.
There's evidence that during these oceanic anoxic events, you actually had that happening within these broad super oceans. So the whole of the Pacific might have been euxenic, as we call it, devoid of oxygen and containing free hydrogen sulfide. So these very noxious environments spreading over huge areas of the globe.
The best way to understand just how bad things can get during an oceanic anoxic event is to go for a swim in one. And you can, on a small scale at least, in upstate New York. Lee Kump offered to take me for a dive into oil's poisonous prehistory.
Green Lake's a fantastic place because it's a mesocosm of what anoxic oceans might have been like in the distant geological past.
Dropping down from the surface, Green Lake at first seems quite normal. But then it changes.
You're moving down through 15, 18 meters, the water's getting darker. There's obviously some suspended bacterial life in the water. But around 20 meters, you end up in an environment that's highly poisonous because not only is it free of oxygen, but it also has toxic levels of hydrogen sulfide. It'd be a horrible place for any air-breathing organism to live. If you have a bright enough light, you see that this murky greenish color suddenly transforms itself into this pink or reddish color.
This is no place for a human to linger. The colour comes from the few organisms that can survive in this hydrogen sulfide-rich water. Purple and green, sulfur-eating bacteria.
Purple sulfur bacteria are photosynthetic. They need light, but they also need hydrogen sulfide, and they can't stand oxygen. So they live right at this transition between oxygenated and sulfitic water, where both of the things that they find essential are available.
Beneath this thick band of bacteria, the lake turns pitch dark and deadly. A perfect tomb for organic carbon.
That environment, we think, was what the deep ocean was like during these oceanic anoxic events.
Scale Green Lake up to the size of the planet, and it's easy to see how broad swathes of the deep ocean became a giant plankton graveyard. A graveyard into which every dead or dying organism sank without decay. This is what was so special about the major episodes of oil formation. The oceans were dying from a double whammy of suffocation and hydrogen sulfide poisoning. And for as long as sulfur bacteria thrived in the sunlight, many other life forms faced extinction. This was a world with the entire seafloor stagnant and littered with corpses. Whole coastlines stinking of rotten egg gas and death. But here's the twist.
Essentially, the system sort of sows the seeds of its own destruction, because as you bury the organic matter, essentially you're entombing carbon dioxide. So carbon dioxide in the atmosphere and the ocean, they're always exchanging, is drawn down, and the greenhouse effect goes into reverse. The world cools and the oceanic event switches itself off, and you're back to equilibrium. And over a timescale, I would say, of maybe 250,000 years, something like that, from the switch-on point to the switch-off point. So the whole thing comes into a beautiful full circle, and you can see this anoxic event as a way that the Earth reacts to removing the excess carbon dioxide that's vented into the atmosphere.
Of the handful of such events now identified, every one shows the anoxia switch on sharply, as if some threshold of warming is suddenly crossed. And equally suddenly, they switch off when enough carbon has been buried to cool the planet. The burial of excess carbon resets the Earth's thermostat. There is a sharp drop in sea temperature, a drop in sea level, and signs of ice reforming for a time at the poles. And the legacy for us? Another oil deposit entombing all the carbon that caused the problem in the first place.
We find the oil, we burn the oil, we push carbon dioxide back into the atmosphere, and essentially we push the planet towards a greenhouse future.
Of course, crude oil is only one source of the fossilised carbon we're adding to the atmosphere. But it's crude that allows us to mine coal so easily, and crude source rocks that produce our natural gas. It's crude that has allowed us to clear forests and spread out over the surface of the Earth with such speed and in such numbers. It's crude that underpins the growth that keeps economies solvent. In short, crude drives the civilization that pumps the gas.
If you look at the historical records of the atmospheric CO2, you can see us undulating along in the last ice age, coming out of the last ice age, and then coming up towards the present, and you reach the last century, and it suddenly, this spike goes through the roof. And it is probable that the Earth has never experienced a rate of increase of CO2 in the atmosphere at anything like this rate in its history.
It's a rate that might be ushering in not just global warming, but the next super greenhouse. The evidence suggests that the overcooked worlds of the past were triggered by levels of CO2 about 4 times higher than those at the start of our industrial age. But while it took volcanoes thousands or even millions of years to achieve these levels, we're on track to reach them in 100.
What we're doing is upping the ante by accelerating the rates of natural processes by 100,000, 10,000 times. So we're probably to that extent mimicking phenomena that have happened in nature, but at this incredibly accelerated timescale.
In 2006, southern England sweltered under record-breaking July temperatures. It might have been the first flush of a Jurassic climate returning to the Jurassic coast. Meanwhile, carbon dioxide levels continue to rise, heading for twice pre-industrial levels by the middle of the century. Around the world, the signs of change are making themselves apparent. No one knows at what point we might cross a threshold that switches us into real climate trouble. The guesstimate the world is banking on is that we can escape catastrophic change if we can stop CO2 concentrations from more than doubling. But this assumes there are no surprise amplifying effects waiting in the wings. And it's clear from warming signals in the Arctic, change can be unexpectedly rapid.
Much of Greenland has changed rather dramatically, much more dramatically than any of us would have thought 10 years ago. The icebergs you see behind me are all from Jakobshavn Isbrae, Greenland's largest outlet glacier. In about 2000, the glacier began speeding up and is now flowing at about twice the rate it was in the mid-90s, which means it's now putting out something like 50 to 60 cubic kilometers of ice a year, which is going to have an obvious impact on sea level rise.
It's this sudden loss of polar ice, both from the land and particularly from the sea, that has the potential to amplify warming and nudge us more swiftly into a hothouse future. As temperatures rise, there is less shiny white ice left to reflect heat away, and more dark Arctic Ocean ready to absorb it. The faster the sea warms, of course, the quicker the remaining ice melts. It's the sort of feedback loop that could help flip the switch on ocean circulation, and perhaps set the stage for the next major phase of ocean stagnation. Already, scientists report signs that the Gulf Stream has begun to weaken. And in late 2004, part of the current actually shut down for 10 days.
We would like to be able to conclude that these types of consequences are just buried in the distant geological past, but in fact, at least the early stages of widespread oceanic anoxia is where we're probably heading with fossil fuel burning. In terms of the concern that humans should have for the alteration of the environment that supports us, it's certainly on the timescale of concern.
As the human population climbs towards 7 billion and the desire for first world affluence spreads across the globe, we're burning oil as fast as we can pull it out of the ground.
Cars and suburbs and roads and that whole model of sprawl, which is based on sort of the bounty of oil, is starting to spread to China and India, where they're actually on this frenzy of road building. You know, so in Shanghai, for example, they don't even allow bicycles anymore in Shanghai, in the city. When the Chinese people start driving cars the way we do, then we'll have long passed the tipping point for, for climate change.
The thirst for crude is pushing civilization simultaneously towards two perilous futures. In one, the flood of cheap energy we've taken for granted will dry up faster than we can adapt. In the other, our headlong rush to use the last of the resource could plunge us into an unpredictable climate catastrophe. On the face of it, you might expect that running out of this stuff will at least save us from the climate threat.
The latest work of the climate scientists on this subject, the Intergovernmental Panel on Climate Change, says that we can afford, I use that word in inverted commas, if you make certain assumptions about the amplifying factors, the feedbacks in the system, we can afford to put into the atmosphere another 400 billion tonnes of carbon. Well, you just look at what's left in fossil fuel reserves below ground. You've got 700 plus in oil alone, if you count the regular oil, and just a bit of the easily accessible unconventional oil like the Athabasca tar sands. Then you've got 500 billion in gas and coal. Forget it. It's 3,500 billion and counting. So we can cook our planet many times over if those assumptions are right.
Jeremy Leggett spent much of his early oil industry career at the prestigious Royal School of Mines in London, training others in the fine art of finding oil. The threat posed by climate change prompted him to switch camps, first to Greenpeace, and more recently to lead a UK company providing solar alternatives.
My abiding fear is that I'll live through what remains of my vocational life in an exciting, fast-growing company while the world is going to hell in a bucket because of the stupid addiction to oil that we've had all these years and the effect it will ultimately have on our economies after the peak of production and the collapse in supply. Plus, of course, the unfolding effects of global warming, which just get worse by the month.
Pumped from its hiding place beneath the Arabian desert, our carbon atom is once more playing its part in the great drama of life on Earth. Meanwhile, the second half of the Earth's endowment of crude lies underground, waiting for the human race to suck it up. Somewhere ahead, one way or another, the end of the oil age is coming.
Our whole civilization has evolved in an era of stable climate, which is probably anomalous in terms of, if you look at it over geological time. So was this our moment in the sun, which is now coming to a close? That's sort of a pessimistic view, but I think perhaps could be true.
Really and truly, you've got to be a flat earther not to see what's going on now and what's being projected by all the scientists studying climate. If we keep going as we are, we will wreck our economies and wreck our planet and really completely decimate ecosystems.
Well, I claim that our grandchildren are going to look at us and say, you burned all that oil, all those nice molecules, you just burned it? And we'll have to admit we just burned it.
Oil is a precious thing. Fossilized sunlight captured by tiny, brainless organisms that lived for a mere instant in geological time. Yet every year we burn more and more of what we have less and less of. Are we mining the aftermath of past climate catastrophes simply to engineer our own? It would be ironic indeed if the end of our oil age becomes the start of the Earth's next great phase of oil formation. One thing is clear, love it or loathe it, we've all become part of oil's extraordinary story.